Now, this problem is on radioactivity and half-life. It says a substance obeys the decay equation. N of t is 80,000, 2 to the minus 0.00068 t, where t is measured in years. And then it asks you some questions. What is the half-life of this radioactive substance? B, how many years will it take to decay to 1/32 of its original value? C, how many years will it take this substance to have 3,700 active nuclei? And then D, how many active nuclei will remain after 12,000 years? Okay, so it asks you some various questions which are typical of half-life questions. So first of all, it gives you the equation. So what would be the half-life? Well, the half-life is defined as the time that it takes for half of the original active nuclei to remain, right? So originally there's 80,000. How do we find the half-life from here? Well, as long as this thing is equal to 1, right, what's going to happen? It'll be 2 to the power negative 1, right? And if it's 2 to the power negative 1, it'll be n of t 80,000, 2 to the power negative 1. That means 1/2 of 80,000. That means 40,000 active nuclei will remain, right? So in order to find the half-life, we set this thing equal to 1, and then we solve for t, right? So we say 0.00068 t is equal to 1. T is equal to 1 divided by 0.00068. Okay, so what is that equal to? 1 divided by 0.00068. 1470.588 years. So about 1,470 years is the half-life of this substance. Okay, the formal way to write this equation would be to say n of t is equal to what? 80,000, 2 to the power negative t over tau. Okay, 2 to the power negative t over tau. Tau is the half-life. Tau is half-life. Okay, so in other words, notice here from this equation, tau is the reciprocal of this number. And that's exactly what we did. You know, okay, we could call this tau. Notice we took 1 over the reciprocal of this, and then that's how we could say it. This is the half-life. When t is equal to 1 of tau, 1 tau, then half of it will remain. When t is equal to 2 tau, 1/4 of it remain, and so on and so forth, right? So in part B, how many years will it take to decay to 1/32 of its original value? Okay, well, the reason it's chosen in this case 1/32 is because it has a particular meaning here. Powers of half, right? What is that? Well, 1/2, if you do to the nth power, what is that? How do you get 1/32? Well, n must be equal to 5, right? 5, that's equal to 1/32, because 2 to the power 5 is equal to 32. So how many half-lives must have taken place in order to only have 1/32? Well, after 1 half-life, when t is equal to tau, 1/2 of the original value will remain, right? When t is equal to 2 tau, 1/4. When t is equal to 3 tau, 1/8. When t is equal to 4 tau, 1/16. When t is equal to 5 tau, 1/32. You see, so therefore the nth power here, the power of the 2 that requires you to get to 32, that's equal to 5. That's 5 half-lives. So 5 half-lives have to elapse in order for 1/32 of the substance to remain. Well, since the half-life was 1,470, we multiply that by 5. So that's going to be 7,352.94 years. 7,352 years must elapse in order for 1/32 of the material to remain, right? How much material will that be? 80,000 divided by 32. 80,000 divided by 32, that's going to be 2,500, right? So at that time, only 2,500 active nuclei will remain, okay? Question C, how many years will it take this substance to have only 3,700 active nuclei? Well, it should be less than 7,000 years, right? As you notice here, 2,500 active nuclei will remain after 7,300 years. If I want 3,700 active nuclei, so it's going to be a little less time than this, right? So how do we do that? Well, I put 3,700 here, 80,000, 2 to the power negative 0.00068 t. I could get rid of the 2 of the zeros here. Then I'll have 37, and then bring down the 800, 2 to the minus 0.00068 t. So if I want to know what t is, what am I going to do? I could take the logarithm of both sides, or the natural log of both sides, right? So log of 37 over 800 base 10. If I take the log of this, log of base 10 2 to the power negative 0.00068 t, what will happen? This power will come down, and you will just have log of 2 remaining. So log base 10 37 over 800 equal to negative 0.00068 t log 2 base 10. Okay, let's erase some more. Now, notice what? The log of 37 over 800 is going to be negative, right? So I could actually take this negative, take it over there, and then I could switch the power, right? So you need to know several of the properties of logs in order to be able to do this problem really. Log of a to the nth power is equal to n log of a. So basically, this negative one goes over there. You see, this is the n here. And it goes over there to the power. And then this becomes reciprocated, right? And then therefore, you get rid of the negative here. So therefore, what's the final answer? You have, this is going to equal log base 10, 800 over 37, divided by log of 2 base 10, and then divided by all of this, 0.00068. That's going to equal t. That's how many years it will take to have 3,700 active nuclei, and I predict that it's going to be a certain time less than 7,000 years. Okay, so let's take log of that. So 800 divided by 37 is some random number. Then let's take log of that. And then let's divide that by the log of 2. Now I could also take the natural log, ln, as long as both of them are natural log, right? So that doesn't matter. So ln of that number divided by ln of 2. And then divide this by 0.00068. Okay, and then the answer that I get, 6,521.18 years. Okay, so that is the answer. This is a little bit less than 7,352 years, right? Now, what was the final question? How many active nuclei will remain after 12,000 years? So in this kind of question, we want to know how many nuclei will remain after a certain time, whereas in the previous question, we wanted to know how many years it will take to have a certain number of active nuclei, right? So basically all we do here is we just put the 12,000 into the original equation. So we have n of t, that's 80,000, 2 to the power negative 0.0068 times 12,000. 279.695 active nuclei. Well, that's quite a lot of half-lives, right? So by then only approximately 280 active nuclei have remained. Now not much of the substance has remained. So you can see the basic radioactive questions will have these kinds of questions to it. What is the half-life? How many half-lives will it take for it to decay? What is the number of active nuclei after a certain number of years, and so on and so forth. So some basic knowledge of logarithm is sufficient to be able to solve problems like this. Okay? Thank you very much.